everybody. I want to take you through a set of steps that I think will be useful for doing this coursework. So to start off with, the objects that I've given you include an AND gate, an OR gate, and a basic event. So at the moment these objects are empty, essentially. They just allow you to create them, and also the example fault trees object allows you to build a set of fault trees from them, but none of the drawing code is available. So let's just move those to one side and start with the AND gate. So when I was drawing my AND gate, what I did is I defined an area in which I wanted the AND gate to fit, and it was centered around 0, 0. So essentially what I did is I defined a 100 unit square where I could draw my AND gate in. So let's just do that. What I did is I added a little stick at the top, a little stick at the bottom, so that I could connect them to other gates later, and then I drew, a bit sketchy here, an AND gate using the line to, move tos, and arc functions. Okay, so now my AND gate has a draw function. Notice that I didn't give it any sort of position data because I'm just drawing it about 0, 0. The position is going to be given by some parent gates later. So let's just put that AND gate aside. My OR gate, same deal again. I defined a 100 unit square, and it was centered about 0, 0 at the origin. I added my little sticks in. Need slightly bigger ones for this because of the way that it curves. And then I added, using Bezier curves, my AND gate drawing. Oh, sorry, my OR gate drawing. Okay, so there's an OR gate, and then basic event. Again, centered about 0, 0 in the middle, 100 unit square. A little stick to attach it with. I drew my circle to signify basic event. So those are the three main ones. There's also, I forgot to mention, transfer gate, which is actually more like a basic event than a gate. And that has your triangle. Again, I made it so that it's centered on the origin, 0, 0, and all fits within a 100 unit square. Okay, so now I've got my basic tools. Whenever I want to draw one, when I was testing them out whilst I was drawing them, I just sort of said, okay, well, here's my canvas. I'm just going to make a new, got my origin in the center, just pretend that's in the middle for now. I said, okay, AND gate equals new AND gate, AND gate.draw, and then it would appear in the middle of the screen, in the middle of the canvas. And the same applied for all of the other things. Transfer gate.draw. Obviously I had to instantiate each one of them before I could draw them. Basic event.draw. OR gate.draw. Each time, because there was no position data given, it drew in the center of the canvas there. Okay, so that's the easy part out of the way. I can now draw all of my objects. So what I want to do next is I want to have some test fault trees in order to do it. So in the most simple case, we have the first fault tree in the list. So if you do example fault trees dot get fault tree open brackets, 0, close brackets. That gets the first fault tree in the list. And what that gives you, I just get my Blue Peter, here's some I made earlier. It gives you these objects all connected together. It has a top node that is an AND gate. That has two children, which are OR gates, and each of those OR gates has two basic event children. So those, as it stands at the moment, when you get hold of that top node, that is what you get given. So let's do that. Let's start with our top node, which is an AND gate. So when we say top node.draw, that's what we get. AND gate in the middle of the canvas, because that's what we have in our drawing code at the moment. We can draw an AND gate centered around the origin, and that's what we have. So the next thing that we need to do in order to make this work is to draw all of the children of that gate. So what we can do is we can just set up a for loop that goes through all of the children in the AND gate, because if you remember, AND gate and OR gate both inherit from the fault tree gate type. So fault tree gates have an array inside them called m children, and this array contains fault tree nodes in it. So any children of the gate are held in that array, and there are utility functions there, num children, which gives you how many children are in that array, and there's also get child, which you give an index parameter which gives you the child at that index. So using those two functions, you should be able to list through all of the nodes in the array. So that's what we're going to do here. So in the first case, we'll say for each child in the top node, which in this case is an AND gate, draw child, so child.draw. So we'll come along and we'll say, okay, well, the first child is OR gate. And then OR gate also belongs to the fault tree gate parent, so it has a draw children method in it as well, or it will do once you add it. And when that's called in the OR gate draw function, it will draw its children, which are two basic events. So we're going to draw those, child and child again. Then we'll come back up, draw the second child of the top node, then we'll draw its children, basic event, basic event. Okay, so now we have drawn our entire tree. Every one of the items in our tree has drawn. Now it won't look exactly like this because I can't sort of mimic the transparency with my printouts here, but simply what you would get is all of your nodes drawn together on top of each other in the center of the canvas. Because we haven't included any code, any transformations in order to spread them out a little bit. So we've made a good first step in that all of our fault tree is now drawing, it's just not looking exactly how we want it to. So the next step is to start looking about how we're going to spread out our tree. So in order to build up this tree, we're going to need to know how to draw the children in the right place. So there's a nice simple algorithm that you can use, which is generic, so it will apply to any set of children. So in the first case, let's draw the first child of this AND gate. I'll move that out of the way for the moment. If we're drawing the first child, which is an OR gate here, it has its two basic event children. So if we just drew our children one after the other, without any translations, they'd all appear in the middle, like before. So the first thing that we're going to have to do is to translate them down by one height. I say one height because when I drew all of my node types, I made sure that they all fit in the same bounding box, 100 by 100. So if I translate it down by a height, one single height unit, which in this case is 100, then it appears exactly below the previous one. So at this point, we've got our first basic event drawing underneath the parent gate. But we want to start off by actually translating it half of its width along. This is because we're going to need to do some corrective transformations later. But this is the starting one, so the first node translates across by half of its own width. Then, in order to draw the second child, we need to translate it by the remaining half of that, so we've translated it the full width of this first child, plus half the width of itself. So now the two appear side by side. Next we need to get it to appear centrally underneath the parent gate, so we translate it by half the total width of all of the children. So all these sibling children, we have to translate it by half of that width. So if we do that, then this is what we end up with. An OR gate with two basic event children centralized underneath it. So if you remember, our original AND gate had two sets of children that looked like that. So the same algorithm would apply for drawing both of them. But how do we draw them relative to each other? So I'll move them out of the way for the moment and come back to our top node, our AND gate. So in order to draw the first child, we take it, we translate it so that it's one height down from the top node, and then we need to translate it by half of its total width in the x direction. So the total width of this is given by the total width of all its children. So in this case it has two basic events, both of which are 100 units wide. So we have our OR gate say, okay child, how big are you? I'm 100 wide. So the first child is 100 wide. He asks the second child, how wide are you? I'm 100 wide. So by adding those two together, the OR gate knows that its children add up to 200 wide, 100 plus 100. So now its total width is 200. So we translate it by half that total width, and that positions it here. Next, we do the same with the second child. We want to translate it by the remainder of the half of the width of the first child, so it's translated the full width of the first child plus half of its own width. Remember, we calculate its own width in exactly the same way by asking the children how wide they are and adding them up. I'm 100, I'm 100, that makes 200 in total, so we translate it across by 100 again, and that positions it neatly beside the first child. Then we want to translate it by minus half of the total width of all the children. So remember how we get the width of the children. We ask each child, how wide are you? I am the width of my two children together. 100 plus 100, I'm 200. Second child, I am the width of my two children put together, which is 100 plus 100 is 200. So both of those together is 400, and we translate by half of that distance, minus 200. And that positions all of our nodes neatly underneath the parent gate. Now the trick to this is that because the translations have to happen before you call each of the drawing codes, you're going to need to calculate the total widths of the children before you do the translations. So these actually happen in the code in a slightly different order. So in terms of the order of the actual code, this is going to work slightly differently. Because you need to do the transformations in a particular order, you need to know what the widths of all the children are before you actually draw them. So in the case of drawing this simple tree, we draw a top node in the middle as usual. Then before we can start drawing any of the children, we need to know the total width of the children. So we ask each of the children in turn, how wide are you, and add them together. So our OR gate, our first child is an OR gate, and we have to ask it how wide it is. So it says, oh, I don't know exactly, I'll have to ask my children. So it asks its children, two basic events, how wide are you? First child says, I'm 100 wide. Second child says, I'm 100 wide. So the OR gate adds them all together, and it says, I am 200 wide in total. Then it asks the next child, which is also an OR gate, how wide are you? It says, I don't know, I'll have to ask my children. So it asks its first child, a basic event, how wide are you? I'm 100. Second child, how wide are you? I'm 100. So the OR gate says, adding those all together, I am 200 wide. So now the top node knows that the total width of all its children is 400, which also happens to be the width of this piece of paper. So we'll move those to the side again. So now, when we are drawing our first child, the first thing that we need to do before we draw any of the children is to translate half of the width of all the children. So in this case, we'd be taking our children and translating it by half of that 400, the total width of the children, which brings us to here. So next, when we draw our first child, we will draw it there, once we've also translated it down the height. Except that we want to translate it by half of its own width as well. So in order for us to know its own width, we need to ask it, how wide are your children? So again, they say, I'm 100 plus 100 is 200. So I need to translate this half of its children's width back in the other direction. So now we have it placed. To draw its children, we apply the same process. We ask, how wide are all of your children put together? Well, we know that's 200. And I need to translate by half of that distance in the other direction. So we go back, which brings us to here. So we would be drawing there, but we need to translate this child by half of its own width back in the other direction. So there we draw it. Then we draw the next one, the other half of its width plus its own half width, which draws it there. Then back up to the next child of the top node, we have the OR gate, which is all drawn in place because of our original translation. We need to translate this by the width of the previous child plus half of its own width, which if you remember is 200 because it has to ask its children. It can draw its child as plus half of that width. Same with the last one. So you can see how the order that you call the translates requires that you work out what the width of the children is before you actually call the drawing. For this next part of the video, we're going to try and build up this fault tree here step by step using the algorithm that we've previously sorted out. So this is the second fault tree in the list of example fault trees in the objects that I've provided for you. So let's build this up through the algorithm. So if we want to draw this larger fault tree, we need to start with the top node. So we have OR gate, which we draw in the right position. The next thing we need to do is start drawing its children. But like I said before you can actually draw any of its children, you need to know how much you need to translate them across by, which means calculating what the width of all the children is. So we do this using a depth first traversal of the tree. So we ask the first child, the top node, how wide are you? Well, being a gate, it doesn't really know how wide it is, so it asks its children how wide are they. So the first child is a basic event. Basic events know how wide they are because they're terminal nodes, they don't have any children. So it just returns and says, I'm 100 wide. Next child, also a basic event, says I'm 100 wide. Now the running total is 200 wide for this gate here. Final child returns I'm 100 wide. So now we know that the total width of this gate is 300. So it returns the value 300 to the top node. Top node asks its next child, how wide are you? Well, it's an AND gate. It's a fault tree gate, so it doesn't know how wide it is. It needs to ask its children. So it asks its first child, how wide are you? Well, that's a gate as well, so it asks its children, how wide are you? This is a gate as well. It asks its children how wide it is. And its first child is a basic event, so it returns 100. I'm 100 wide. Second child, I'm 100 wide. So now we're 200. I'm 100 wide. Now we're 300. So this gate is 300 wide. It returns 300 to its parent. Parent asks its next child, how wide are you? That's 100. So that's 100 plus 300 is 400. So next it passes that 400 back to its parent. Its parent asks the rest of its children, how wide are you? It's a basic event. It says 100. So 100 plus 400 is 500. So this is now 500 and returns that to the top node, which also adds that to its previous child. So the total width of all the children of the top node is 800. 300 plus 500. Next, we need to translate half of that 800 across. Just so happens to be the size of this piece of paper. So we will translate 400 across. So that puts our current drawing position here. So if we were drawing the next child, then we would be drawing it there. But now we need to apply that same algorithm again. We need to know how wide are all of the children of this node. Well, this is what the child looks like. It has an OR gate and 3 basic event children. So to know the total width of this child, we need to ask its children 100, 100, 100, total width 300. So we want to translate that OR gate half of the total width back in the other direction, which we can do like this. So now that child is correctly drawn in place, and we can start drawing its children. If you remember, the first step for drawing the children is to translate half of the distance of all of the children back in the other direction. So if we translate that by half the distance, that would take us to here, except that now, to here, except that we want to translate by half of this distance back towards the centre. That brings us to there. We can draw the next child along at this point, translated the distance of the previous children plus half of its own width, and the final child by the distance of the previous children plus half its own width. And there we have that child completely drawn. So if we replace that with the fully drawn version, that's where it ended up. So next we're going to do this part of the tree. Now remember that it's already been translated across like that, so we need to start building up. Where is this AND gate going to be? Well, the AND gate's position depends on the total width of all its children. So we can ask all its children. If you remember from before, we just progress down the tree. 300 plus 100 plus 100 is 500. So we need to translate that half of 500 along from the previous width of the earlier children. So this piece of paper is 500 long, so if we translate by half, then that is where we'll put our AND gate. Next, we're going to be building this part of the tree. So we ask for this child, where are you going to be positioned? Well, we need to know the total width of all of the children. So that's the 1, 2, 3, 4, 5. So we're going to translate by half of that distance. Which brings us to here. But then we need to know what is the width of all of your children. Well, if we ask it what its width is, we'll end up with 400. So we can translate back half of that distance in the other direction, like so, which brings us to there. So that's where our OR gate is going to draw. So we can start drawing its children now. Remember, its children look like this, first child at least, and we need to add the width of that as well to get the total width of all its children, which is 400, and translate across by half that height, half that width, sorry, which is here. So that's our drawing position. But we need to translate back in the other direction of half of the width of this child. Which brings us to here. So we can take another OR gate and put it in that position. Next we're going to build its children. They're all basic events, so they all know their own width, but we need to add up the total of them, which is 300. We need to translate it by half that width, which brings us to here. And then translate that child by half its width. The other direction gives us the first position. The next child is translated the width of the previous children plus half of its own width. And the next child is the width of its previous siblings plus half of its own width, draws that. So we finish that part, we're backtracking up to the next child of this gate. So we already have a position for it because it is translated across the width of the previous child plus half of its own width, which puts it there. This node is now complete. Backtrack up to its parent. We need to add another basic event. So we position that it translated across the width of the previous children plus half of its own width, which draws it there. And that is the complete fault tree drawn, using the translates in the correct order.